I'm Mary Fenlon. I'm the product manager for optimization here at MathWorks. And I've worked on optimization and optimization software for a long time, and I really love to see what people can do with it, how it can result in better designs and better decisions. Shahini?
Thanks, Mary. I'm the product management lead for math and optimization here at MathWorks, and I have had design optimization experiences even before joining MathWorks, and I'm here excited to show you what you can do, how you can use optimization to improve your designs.
Okay. So Shahini, before we get started, did you see this latest meme from the Global Optimization Toolbox, this latest tweet?
No, I haven't. What's this about?
Well, it's using the how it started, how it's going meme. And how it started is there's an initial design for a Yagi-Uda antenna. And what you really want is to see dark red way up in the Z direction. And well, that initial design, it's okay. But once we apply optimization, we automatically found a good design. And so it's nice and dark red. It's really high in the Z direction, not so high, not so strong in the X and Y directions. That's what you want. You want high directivity out of an antenna design. So that's the kind of thing you can do when you apply optimization. And we're going to see more of that today. So what other kind of things can you get out of doing design optimization? Well, we talked about finding a better, improved design, but you can also reduce the time of design iterations by using this automated process of optimization. It can help you understand the design space, find the non-intuitive designs, automate design work, and result in lower cost designs. So these are some of the kind of things we'll talk about today. As we've talked to engineers, what we've seen are this kind of a workflow where you start with a design model. You might have to refine that model with parameter estimation by estimating some of the parameters to match your real-world data. And then you want to explore the design space, and this can be done with design of experiments, some global sensitivity analysis, get an idea of what the model is telling you. And then you can apply some formal optimization techniques. And that's what we're really going to focus on today. We'll talk about some of the other steps as well, but we're really going to focus on applying optimization to that design model. So we make an optimization model on top of the design model. And then we'll also briefly talk about some of the analysis and reporting that you might want to do once you get some candidates for your design out of the optimization step.
So here are some of the challenges that our engineers encounter while applying design optimization techniques. Now, the first group is about how to set up the optimization problem. How do you formulate the objective? How do you connect multiple models? And the second is about what if the design is time consuming? How do you get it done in time? And the third is about analyzing and understanding the results and sharing the results with others. And we'll show you some of the ways that you can meet these challenges. Now, but before we do that, we would like to know what kind of problems have you encountered in your design optimization project. So we are going to launch a poll. And there are some options there. The first three are about setting up the problem, understanding, and connecting different models. The fourth is for doing it in time, getting it done in time. The fifth is understanding results, and anything else that you can think of. So let's take a few seconds. The results are coming in. By far, formulating the problem seems to be going strong. So while they're finishing it up, let's continue with our presentation. So nearly any design can be optimized for a better performance, for a lower cost. So think about your design projects and where you can apply optimization as we walk through these 4 case studies. So we are going to close the poll now. And it seems like, yes, about 30% says is number 1, formulating the problem. And in the second place is 23% of choosing solvers and options. Okay, we'll go through some of the things for that. Closing the poll now. All right, so the first is about designing a disk break. Mary, how did that go?
So first you need to have a model of your design. Do you have that, Shahini?
Yep.
Something that we can use in MATLAB?
Yes.
All right, that's great. So once we have that design model that we can call from MATLAB, we need to formulate an optimization problem around that. And so we need design variables. That's the parameters that you can change. We need an objective function. That is the way you evaluate the goodness of the design or the badness of the design. And then you need the constraints, because sometimes there are things that restrict your choices. Could just be bounds. It could be some more complex physical constraints or balance constraints, material balance constraints. What are these for your problem, Shahini?
So the variables for my problem is really the geometry parameters, the number of holes, the diameter, the thickness of the disk, and things like that. And for the objective, we can use volume. It represents the weight of the material and also the cost. So we have to minimize those things. But also we have to minimize the stress in the disk break. But for that, we have a limit that we can't exceed.
Oh, well, then that makes it a constraint. If there's a limit you can't exceed, that's a constraint.
Okay.
And so do you have some bounds on some of those variables? Because that
Yes.
really helps the solvers.
Yes, I do
Okay.
have lower bound and upper bound.
Okay, so those are going to be our constraints. So now we have to get that into MATLAB.
How do I do that?
Well, let's go to MATLAB and I'll show you.
Okay.
So we start with getting the data set up. So we've got a thermal profile that we generated with Simscape. And then we load that in, and now we're going to use the optimized live test to help us guide the optimization. And this is something you get in a live script. We're using live scripts here. And then you just indicate what kind of things you've got. So we've got a nonlinear function with upper and lower bounds on the variables, a nonlinear constraint, and integer variables. So the two solvers that we can use are the surrogate solver and the genetic algorithm. The choices are limited just to the ones that are suitable for that kind of a problem. So once we have to specify our objective function. Well, so how do we do that? Well, this optimized task is going to give us a little idea. So if you say you want a new one, it generates a template function. So for something with the surrogate, we need to return the objective and the constraint value together. And so we built a function following that template. Here it is, where we call out to SolidWorks to generate the geometry. We read the results in then, and we solve two PDE problems, one for the thermal and one for the stress. So that's all set up. So we're going to use that function from the file. So we'll go pick that one up. And now we have to add the rest of the data. So the heat profile, we have to indicate some of the number of variables, the bounds, the lower bounds, the upper bounds. Oops, wait, I did the wrong one there. Okay, get the right one in there. The upper bounds, and then we've got some integer variables. So we say which one is the one that can only take integral values. There are some other options that we can specify. So we want to specify the number of function evaluations. For these really expensive problems, that's usually the thing you want to do, is say, you can do the time budget in terms of evaluations. There's some other algorithm settings we might want to use. We could use checkpoints. We could provide initial points if we've already done some DOE, and we could evaluate in parallel. That really saves time. Now, we're not going to do that today because we don't have that parallel computation resources, but we could. We indicate some other things that we want to do, and then now we've got some MATLAB code that we can put into a file to actually run our optimization, and that's what we did here. And we ran it. This took all night. We ran it with the surrogate solver, which runs in phases. Looks like we found the best solution probably in that second phase, but we let it keep exploring to see if there was better. And then we wrote out all the points that we evaluated, all the 250 points that we evaluated, because we want to do a visualization with those to understand kind of what the design space looks at. So we're kind of doing a DOE after the fact. We're looking at how all these points evaluate. So back to the slides. The results were that we did improve the volume significantly. The stress is within limits. So the surrogate optimization was able to find a much better point than our initial design. You might be wondering how the genetic algorithm did. That also found an improved design in those same 250 function evaluations, but not as good of a result. And that's what we see again and again, that when there's a really expensive simulation and you have to limit the number of function evaluations, the surrogate optimizer is going to do a lot better than the genetic algorithm. But both are available, depending on your use case. So with this problem, we needed to use MATLAB's ability to do scripting and call other software to integrate with other software. We were able to do that. The optimized task helped us formulate the problem and gave us some guidance on which solver to use. And then we were able to get a good set of results and visualize them with some of the MATLAB visualization techniques. So for the second one, we're going to look at a 5G RF filter design. Shahini, how did that go?
Yeah, it went very well. So here we are designing a very specific type of resonator called F-bar. The goal here is to find an optimal electrode alignment with respect to the substrate by minimizing spurious modes. And the challenge here is that these 3D simulations are very expensive to run. And if you are running an optimization which requires many, many simulations, that can become computationally prohibitive. But what we did was we used one of our partners, OnScale. They specialize in these kind of problems. They have FEA and CFD solvers on the cloud. Those are specifically architected to handle these kinds of large-scale problems. Now, what we did was we integrated MATLAB's genetic solver directly with their solver, with the OnScale solvers. And that made it possible to directly drive the simulations from MATLAB. And we wanted to find an optimal solution, optimal electrode alignment. And we found that. Let's go to the next one. OK. So the blue curve shows you the smooth blue curve is the best design where the electrode is at an angle to the substrate. And the black curves shows a lot of unwanted lateral oscillations that shows you that it's not a good design. And all of this, the whole optimization required about 3,000 core hours, which was done within less than 48 hours on a 64-core cloud machine. And this was only possible because it was tightly integrated to MATLAB optimization algorithm and because of OnScale specialized solvers. And last year, they also released a MATLAB toolbox, which made it even easier for users to set up the optimization problem and run these simulations directly from MATLAB. Now here we address two types of challenges. One is we use genetic algorithm, which makes it very easy to understand. It's easy to use, easy to formulate. And the direct integration with MATLAB with the external platform that made it easy to run the simulations from MATLAB. And the second problem was the time required for these CAD simulations or FEA simulations, expensive simulations. It was possible because the integration was tight, and OnScale is very good at handling these kind of large-scale engineering problems.
Great. So in this next case study, we're going to look at a different way to handle computationally expensive problems. So this case study is about, it was carried out by one of our automotive industry engineers, and he was working on an electrical vehicle design based on one of the reference models in powertrain block set. And the problem is to choose the gear ratio for the front gears and for the back gears. And you want to maximize fuel economy and acceleration.
Well, hold on. How can you do both? Because I wouldn't expect a car with a good fuel economy to have a strong acceleration.
Well, that's one of the challenges, to do both of those at the same time. So we have to take a multi-objective approach for this problem. The other challenge about this problem is that simulation takes 18 minutes to run. You have to run a couple different drive cycles to test the acceleration. So with a multi-objective approach, you need even usually more function evaluations than you would need, more simulations than you would need with a single objective approach. So those are the two challenges that we're going to be looking at for this problem. So in order to meet the challenge of the long time and the need for quicker simulations, the engineer used model-based calibration toolbox to build a surrogate model. And how he did this is he used model-based calibration toolbox to generate a design of experiments. And then with parallel computing, which is a set of candidate points, with the parallel computing toolbox, he was able to evaluate all those points in parallel and then fit a response model using, again, what's in Model Calibration Toolbox. So now he's got a surrogate model that he can use instead of the real model. And if this sounds familiar, this is just exactly what happened in the first case study, the disk break, except there we were building the surrogate as we were optimizing. Here the surrogate is built first. Now the engineer took this one step further, and he built a lookup table from the response surface model. And the lookup table is even quicker to evaluate. And again, this is something that's available in model-based calibration toolbox. So now he's got something that's really, really quick to evaluate. So let's go to see how he can do that. We'll go back to MATLAB. And so with this one, he wants to use Pareto search is the solver we're going to use. And again, we're going to use it. We set up our data. We're going to use it through the optimized live task. And this is a non-smooth objective because it's a lookup table with linear interpolation. And so we've got a couple choices. We could use Pareto search or the genetic algorithm multi-objective search, but we're going to use the Pareto search. So we then have to, again, specify our function. We want to get the Pareto front. And the objective function here is calling out to a function, the lookup table that we set up. So that's what this looks like here. And we have to return two different objectives, one for the fuel economy and one for the acceleration. So once we do this, this is really quick. We develop this Pareto curve, get lots of points there that are close to the Pareto curve. The results are that we get the points, so the values of the gear ratios, and then the objectives that match those values, the fuel economy and the acceleration. We can plot those again on a different kind of plot where it's the plot of the variables themselves, and then we do the contours of the functions. And what we want is those contours to be parallel when you're on the Pareto front. And it looks like we did a pretty good job of identifying those points. So once the engineer does that, now he has to choose which points from that Pareto curve make sense for the design. Maybe there's some restrictions from the manufacturer, but you've got that whole selection of points that you can use. So with this challenge, with this problem, we met the challenge by using a Pareto search to handle the competing objectives, parallel computing to do the response table, and then lookup tables to be even faster, and that new Pareto search solver for efficient solution. So we go to the last one.
All right, so thank you, Mary. For this last case, we are going to take a look at applying optimization on a conceptual design of a quadcopter. And at this stage of the design, the decisions are on the architecture of the model, about its components and its interactions. And this problem was brought to us by some of our system engineers. The goal was, there were multiple objectives. So the goal was to take a look at these objectives and look at which requirements are difficult to meet, how do we balance the requirements. And additionally, there was one problem of this specific problem doesn't have a model in the traditional sense of the word. So we have to build one to do the optimization and the trade-off studies. So let's go to MATLAB and see how it can be done.
We have to go.
Yeah. Can probably move it forward a little bit.
Sorry about that.
It's okay. All right. So here, this is the system composer, the architectural model of a quadcopter. It has 4 components, and each component has a stereotype with multiple properties. Now let's see how you can set it up in MATLAB. We have different types of design variables: motor thrust, battery capacity, and airframe mass. And we have to maximize some of the things, and we have to minimize some of the things. So it's a multiple objective optimization problem. So the first line actually grabs the stereotype properties from System Composer and brings it into MATLAB Workspace. Now here, what we are going to use is called problem-based workflow for modeling and solving optimization problem. And we are going to first define our design variables as optimization variables with lower bound and upper bound, and use those to build constraints and objective. So as I said, like this is a model, this is our model for doing the optimization, the constraints and the objective. The objective here is, the expression is a weighted sum of objectives. And the weights are something that you can play with, you can change it, and the model is very fast to run, so you can do that very, very fast. Now, let's first try exploring the design space. We are going to use Latin hypercube sampling technique to generate the points between the upper bound and the lower bound of the design variables. And that's not just enough. We have to take into consideration that there are different feasibility constraints. So we take all of that into consideration. We generate the points, and then we use create plot live task. This is something you have probably seen yesterday in what's new in MATLAB and Simulink. This is a live task. We use that to create a 3D scatter plot of the design space. So let's see how that looks.
Oh, Shahini, there's only one feasible point.
Yeah, the blue point, this is just one, but this is a very important information for the designer, that it's difficult to meet the requirements. So let's go back and relax some of the constraints, some of the feasibility constraint, and see how that looks. We redo this section and see, do we get more points, less points? What happens next? So now the blue points, we have much more blue points. So it's good that we have more by relaxing some of the constraints. So next we set up the optimization problem, and then we will run it. So let's run this section and see how it goes. You know that it was difficult to find a feasible point, but our solver found an optimal point, which is great. Now we can assign this point, the optimal point, back to the system composer and carry on with our system analysis. Now, going back here, we address all three problems, three challenges by using problem-based formulation, which is easy to set up, easy to understand. It's a multidisciplinary analysis and optimization problem, and we also use design of experiments to explore the design space. The model was very quick to run, so it wasn't very computationally expensive problem. And we used create plot live task to do a visualization. We did trace studies to understand the system, and we also integrated with system composer directly. So that made it also easier to run the optimization.
Thanks, Shahini. That finishes our case studies. So just wanted to give you a quick overview of the products that we use today to do the design optimization work on top of the design models. And so these are the kind of challenges that we met. So we saw, difficulty to set up. The new optimized live task can help you with that. The problem-based optimization, we've got some ways to handle multi-objectives. We have help with time-consuming using some of these newer solvers, using parallel building surrogates. And then there's various different ways MATLAB allows you to share and analyze your results. So there's a couple more things. There's the optimized live task is available in base MATLAB because there's an optimization routine in base MATLAB, so you can try it out. There's a tutorial on using it in a video, so we encourage you to do that. And then if you've got some time today, the very last hour of today, we're going to do a workshop on the problem-based optimization approach where you can try it out on MATLAB online. So we hope you can join us there. And then in the slide handout, these are all links to some of the other things that you can learn more about optimization. And that's all. Thank you.